Welcome to the session on theoretical principles of qualitative analysis. Under this, we are going to understand the theoretical principles involved in qualitative analysis of mixture of salt, and particularly in this session, we are going to understand only about analysis of cations. At the end of this session, one will be able to understand the principle behind systematic analysis of cations, the chemistry involved in separation of metal cations into different groups, the group reagents for different groups, the principle behind selection of group reagents, the role of solubility product and common ion effect in classification of cations. Before going into the details of cation analysis, let us understand about chemical analysis, which we can broadly categorize into two categories: quantitative analysis and qualitative analysis. If I remind you about volumetric analysis, gravimetric analysis, complexometric estimation, in all those we report the quantity of the sample, quantity of the analyte. So there we can club them under the category of quantitative analysis, where our interest is to understand what is the quantity of the sample, quantity of the analyte. But unlike quantitative analysis, in qualitative analysis, we are not going to question on quantity of the analyte or the sample. What we are interested in, the qualitative, that means only the presence of particular sample or particular analyte. In this case, we are going to discuss the qualitative analysis of inorganic mixture of salts, where we will try to identify cations and anions in the given mixture. So, three salts are there in form of a mixture. We are going to report how many cations are there and how many anions are there, and what are those cations and what are those anions. Of course, we will follow a systematic analysis. But in this session, we are going to understand only about analysis of cations. Before going into the analysis of cations, it is important if a given mixture of salt is given, we need to understand what are the anions present in that, because certain anions, they interfere in the analysis of cations. So before proceeding for the analysis of cations, we need to ascertain what are the anions present in the mixture. So analysis of anions before analysis of cation needs to be done. But in this session we are going to deal with analysis of cation only. The analysis of anions will separately have another session. Analysis of cation. Unlike anions, we will understand there in more detail. In case of anions, there are specific tests which can be performed to identify different anions. But unlike anions, for cations, there is no such, it is not possible to use specific tests to analyze individual cations from a mixture. So because of this difficulty, we need to have a systematic scheme for classification of anions. It is just like different categories or different classes of fruits are there in a basket. You need to separate them, you need to classify them based on their categories. For example, nuts will be under one category, citrus fruits will be there under one category, berries will be there in separate category. So you need to classify those cations. If all the cations there are there in form of a mixture, so the task is to classify them based on their properties. So you are going to understand how this classification of cation is important. So there is a scheme that will divide the cations into different groups, and subsequently we will analyze individual cations from those groups. Now question is, how are you going to classify those cations into different groups? What is the basis? So the basis is solubility product. Solubility product, what I mean by a cation is there in a mixture, you are going to estimate, you are going to identify the cation before. As I have said, since there is no it's not possible to use specific tests to identify individual cations. So what is important is to classify cations into different groups. In order to classify cations into different groups, what we need to add certain group reagents which will form precipitates of those particular cations, and precipitation will only be formed when ionic product exceeds the solubility product. So that is why solubility product plays an important role in classification of metal ions into different groups. Like solubility product, common ion effect is also important in classification of cations into different groups, especially for selection of group reagents. So common ion effect, as you are aware of, the ionization of a weak electrolyte, let's say for example HA. If a weak electrolyte is there and you are adding another ionizable salt Ma, so because of the common ion A in both, since the ion in both A ion in both is common, so what will happen? So this after addition of this ionizable salt Ma, the dissociation of weak electrolyte will be hindered or suppressed or depressed. So this is called common ion effect. For example, sodium chloride is lesser soluble in hydrochloric acid because of the presence of chloride ion in common in both sodium chloride and HCl. So this common ion effect is effectively used in separation of cations into different groups. As I have said, in order to classify cations into different groups, what we need group reagents, so that after addition of those group reagents, those chemicals which we say group reagents, those particular cations will form precipitates. So what is the basis of selecting these group reagents? What are the reagents for different groups? How do the group reagents help in identification of cations group wise? So this group reagent, instead of a specific reagent which could precipitate entire cluster of related metals. So that's what we are going to understand. All those cations present in a mixture can be categorized into 6 groups. In first group, the cations are silver, lead and mercury, where group reagent is dilute hydrochloric acid, which is the precipitant. That means when you add dilute hydrochloric acid, the precipitates of silver, lead, silver chloride, lead chloride and mercurous chloride will be formed. So since only these cations are forming their chlorides, their precipitates in form of their chlorides, so these cations are clubbed or classified under group 1. And this dilute HCl, since it is precipitating these cations in form of their chloride, so this is called group reagent of first group. So like this, we have group reagent for all the 6 groups, and cations are divided accordingly. For second group, cations are mercury, lead, bismuth, copper, cadmium, arsenic, antimony, tin, and the precipitant is, or group reagent is, H2S gas in presence of dilute HCl, so which forms the precipitate in form of sulfides of these metals. And similarly, third group cations are iron, chromium and aluminium, and the group reagent is ammonium hydroxide in presence of ammonium chloride. So they do form their precipitates in form of their hydroxides. So similarly for fourth group, the cations are zinc, manganese, cobalt and nickel, and the group reagent is H2S in presence of ammonium hydroxide and ammonium chloride. So they form precipitates in form of their sulfides. And similarly, fifth group, the cations are barium, strontium and calcium, and the group reagent is ammonium carbonate in presence of ammonium hydroxide, and they do form their precipitates in form of carbonates. And similarly, sixth group, the cations are magnesium, sodium and potassium. They do not have particular group reagent, and ammonium is placed under zero group. So we'll study in detail one for each group. Before going into this, let us understand these salts are available in form of a mixture in solid form. So what we need to do, we need to form a solution so that we can do the analysis further, and for that we need to make a solution of the mixture, and in order to make a solution of the mixture, what we need a solvent. A suitable solvent selection is very important. So what is the order is normally followed. First solvent we try is distilled water, first in cold condition, then in warm condition. Then if the mixture is not soluble in distilled water, then we go for dilute HCl. Similarly in cold condition and warm condition. If it is not soluble in dilute HCl, then we go for concentrated HCl. Same thing in cold and warm. And similarly we go for dilute HNO3, concentrated HNO3, aqua regia. So once a suitable solvent is selected, we prepare our original solution. So once the original solution is ready, so then we go for group wise analysis. We start from group 1 cations. So the group reagent is dilute HCl. So if you add dilute HCl, the group reagent, into the original solution, so the precipitates will be formed. White precipitates of silver chloride, lead chloride and mercury chloride will be formed if the cations of first group is present. What does it suggest? The solubility product of these chlorides, silver chloride, lead chloride and mercurous chloride, are lowest than the solubility product of chlorides of rest of the metals present in the mixture. So similarly, there are certain precautions we need to keep in mind while doing analysis. Lead chloride is appreciably soluble in water and HCl, particularly at higher temperature. This is the reason why lead is found both in group 1 and group 2. So that's why it is desirable to precipitate completely in group 1, because it interferes with tests of bismuth, copper and cadmium. So what is required? The dilute HCl, the group reagent, should be added to cold original solution, because in hot water lead chloride is soluble. Since it is soluble, it will pass to second group. Mercurous chloride being an insoluble compound, unlike mercury chloride, mercurous chloride salt give precipitate in group 1 with dilute HCl. But while preparing original solution in dilute HCl, for prolonged heating of the mixture in dilute HCl, this mercurous ion gets converted to mercuric ion, and that appears in second group. Analysis of group 2. The cations are mercury, lead, bismuth, copper, cadmium, arsenic, antimony and tin. The group reagent is H2S gas in dilute HCl. So when H2S gas is passed in dilute HCl medium to these cations, if these cations are present, then what we get? The sulfides of these cations. So what does it suggest? The solubility product of sulfides of these cations are lowest than the solubility product of sulfides of all other metals. That is why only these cations are getting precipitated, rest are not. Rest are remaining soluble, and for subsequent group analysis we follow them. Certain precautions we need to keep in mind in second group. Strength of HCl should not be very high while passing H2S for group 2 cations precipitation. The precipitation of lead sulfide, cadmium sulfide and tin sulfide is incomplete if the concentration of HCl is too high. So what is needed? We need to precipitate, we need to pass H2S gas in dilute HCl to ensure precipitation of lead, cadmium and tin. And next point you need to keep in mind, strength of HCl should not be too low. If it becomes too low, then sulfides of zinc group may be precipitated. So before passing H2S, the solution should be diluted using water or ammonia. So group 2 should be precipitated from a hot solution because heating favors coagulation of sulfides and its subsequent filtration. Since in second group we have seen number of cations are more, so what is required to divide them into two groups, group 2A and group 2B. How can it be done? By using a reagent that is yellow ammonium sulfide. So what we can do, once we have got the precipitates of sulfides of second group cation, then add yellow ammonium sulfide into it. Certain cations, that is called copper group, they are insoluble in yellow ammonium sulfide, so they form one group. And another set of cations called arsenic group, they are soluble, so they form another group. So copper group, you have mercury, lead, bismuth, copper and cadmium. Their sulfides are insoluble in yellow ammonium sulfide. Under arsenic group, the cations are arsenic, antimony and tin. Their sulfides are soluble in yellow ammonium sulfide. So that's how we can be able to separate these second group cations. Now analysis of group 3. So the cations are iron, chromium and aluminum. The group reagent is ammonium hydroxide in presence of ammonium chloride. So these three cations, they get precipitated in form of their hydroxide. So what does it suggest? The solubility product of hydroxides of these three metals are lowest than the solubility product of hydroxides of all other metals. So that's the basis of group separation. So here also we need to keep certain things in mind. The hydroxides of subsequent metals, in fourth, fifth group metals, can also be precipitated by ammonia, but they are kept in solution by addition of ammonium chloride. So here the role of common ion effect comes into picture. So because of common ion ammonium, so the concentration of hydroxide is maintained. So concentration of hydroxide is released to that much which is required to precipitate only the third group cations, not the higher group cations. So ferrous is incompletely precipitated by ammonia. So that is why it is oxidized to ferrics by addition of concentrated HNO3 after group 2 analysis. Only a slight excess of ammonium chloride should be added, as too much of it does not precipitate chromium hydroxide properly. The group 3 precipitate should be filtered off immediately because a delay in filtration may result into partial precipitation of hydrated manganese dioxide due to atmospheric oxidation. Analysis of group 4. Metals are zinc, manganese, cobalt and nickel, and the group reagents are ammonium chloride, ammonium hydroxide, and then warm them and pass H2S gas, and the precipitates will be in form of zinc sulfide, manganese sulfide, cobalt sulfide and nickel sulfides. So again, what does it signify? The solubility products of these sulfides of these four metals are lowest than the sulfides of all other metals. That is why only these four metals they get precipitated, the rest remain in solution. Let us compare group 2 and group 4, because in both the cases precipitant is H2S gas, but the medium of analysis in group 2 was acidic. In this case it is basic. So how is it playing a different role? Let us understand. In group 2 the medium was acidic, means dilute HCl, and then we are adding passing H2S gas. So in this you can see common ion, that is hydrogen, is common in both. So because of the presence of common ion H+, the dissociation of sulfide H2S into H2 minus is suppressed. So the concentration of H2 minus is lesser, so which leads to precipitation of only group 2 cations. But after group 2, in group 4 the medium becomes basic when we add ammonium hydroxide. So when we add ammonium hydroxide, look at the ionization. So because of here it is not common ion, so what is happening, in fact, OH minus from ammonia and H plus from H2S, they combine to release water, which promotes the reaction in forward direction. That means ionization of H2S becomes more, or you can say the concentration of sulfide increases, which is required to precipitate the group 4 cations. Certain points here: manganese hydroxide is formed when ammonia solution is added to manganese salt. The precipitate is insoluble in excess ammonia but dissolves in solutions of ammonium salts. It is therefore necessary to add large excess of ammonium chloride while precipitating the group 3 cation. Similarly, ammonium hydroxide can precipitate cobalt, nickel salt, but they remain in solution in presence of ammonium chloride. Again, the role of common ion effect is playing role here. So H2S should not be passed for more than 1 minute in this group, as in presence of too much of H2S, nickel sulfide partially forms a colloidal solution and escapes in the filtrate. So we will miss nickel in group 4. Now analysis of group 5. The cations are barium, strontium and calcium. The group reagent is ammonium hydroxide and saturated solution of ammonium carbonate. So the cations, they form precipitates in form of their carbonates: barium carbonate, strontium carbonate and calcium carbonate. Again, what does it suggest? The solubility product of carbonates of these cations only are lowest than the solubility product of carbonates of all other metals. That is why these are classified under group 5. One thing we need to keep in mind here: the ammonium carbonate, when we are using, need to be used freshly prepared, because if it is prepared before this ammonium carbonate, so the decomposition of ammonium carbonate into ammonia and carbon dioxide may not give proper result. So analysis of group 6. Cations are magnesium, sodium and potassium. There is no common precipitant or reagent for magnesium, sodium and potassium. Therefore these cations are directly analyzed through flame test. Although manganese resembles with calcium group, it is not insoluble in presence of ammonium chloride, so it is not kept in group 5. Though magnesium forms some insoluble salt, sodium and potassium form practically soluble salts with a very few precipitates. About ammonium. Ammonium cannot be analyzed in group 6 with other alkali metals and magnesium, because this is analyzed separately directly from mixture, simply because if you recall, for separation or classification of cations into different groups, we have added ammonium hydroxide and ammonium chloride on our own. Since we have added ammonium ion into mixture, so it will be meaningless to go for taste of ammonium from the original solution at group 6. That is why it is directly tested from the original mixture of salts. A group reagent separates the cations of particular group only from the group which follow it, not from those which precede it. Therefore, one group has to be completely precipitated before proceeding for the next group. All precipitates must be washed to remove adhering liquid in order to avoid contamination by metals remaining in the filtrate. Thank you.